Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss. Let me write the topic in, I think, green. Our topic is the Maxwell Boltzmann Boltzmann distribution of speeds. This is our today's topic. Let me adjust it. Okay. The Maxwell-Boltzmann distribution of speeds. Let me underline it. One line is sufficient. So let us discuss it. In the last lecture, we defined Maxwell-Boltzmann gas. Then we talked about the validity of Maxwell-Boltzmann dilute limit. We talked about the degeneracy parameter A. We calculated that A for the situation of helium-4 gas at 1 atmosphere pressure and at a temperature of 5 Kelvin. And we said that the condition for the validity of Maxwell-Boltzmann dilute limit is that the degeneracy parameter A must be much less than 1. And we calculated it for helium-4 gas at a given pressure and temperature, which I discussed already. That turned out to be less than 1. That turned out to be 0.09 in that case. Then we talked about other gases, and we justified that for other gases it will be further less than this value, 0.09. So we are justified in using Maxwell-Boltzmann statistics for real gases. Today, we are going to derive the distribution of speeds of gas molecules in an ideal gas, which is called the Maxwell-Boltzmann distribution of speeds. As you know, the distribution plays an important part in the kinetic theory of gases. Now we want to today derive it. So let me define first my symbol. N of V delta V. What it denotes the number of molecules which have scalar velocities, that means speeds, which have scalar velocities or speeds between v and v plus delta v. So if this n of v, delta v denotes the number of molecules which have speeds or scalar velocities between v and v plus delta v in a gas, in an ideal gas, we want expression for this. We want to express this number in terms of the relevant parameters. That expression for n of v delta v is called the Maxwell-Boltzmann distribution of speeds. When you use Maxwell-Boltzmann statistics to figure out this number. Now we are going to use Maxwell-Boltzmann distribution. So this number can be easily found from the simple idea. We can write Ni equal Gi times Fi. So this is the guiding equation to find or figure out this Maxwell-Boltzmann distribution of speeds. As I told you, Fi is the filling factor, Ni is the number of particles in Gi states, and Fi is the average occupation per state, average occupation number per state. So instead of Gi, we have to write the corresponding density of states function. So what we do, let me first write the expression. We have to write, we'll use another color here. So from this equation, Ni is equal to Gi Fi, this guides us easily. So N of V delta V, we have to first write the expression for density of states. We will write first, it is G of V delta V times the filling factor or Maxwell-Boltzmann distribution, that is A exponential of minus epsilon of V by KBT. I will call it first. What is G of V delta V? I think I will write it here. G of V delta V is the number of states in the range delta V. That is, it is number of states existing between V and V plus delta V, that is in the range delta V, right? N of V is the density of particles in speed V. G of V is the density of states in speed V. So if we are interested in finding N of V times delta V, that is the number of molecules which have speeds between V and V plus delta V, we have to take G of V delta V, that is, we have to take the GI, multiply it by the filling factor. Our filling factor is the Maxwell-Boltzmann distribution, which is A exponential of minus epsilon of V by kT, where here we are expressing this energy epsilon as function of speed. Now, how to do it? We have to simply take our density of states function in scalar k, that is g of k delta k, which we have found by fitting waves into the box. What is the expression? V by 2 pi cube times 4 pi k square delta k. What is V? V is the volume of the gas. What is G of k delta k? It is the number of states in k space in the interval delta k. So it is given by V over 2 pi q 4 pi k square delta k. But we don't want G of k delta k, we want G of V delta V. So what we do, we have to make the transformation. Let me use another color. So what we have to do, we have to take our G of k delta k, we can convert it into G of V delta V. For that, what we have to do, we have to use the transformation. H bar k is mv. M is the mass of the gas molecule. V is its speed. So mv is its linear momentum. H cross k, sorry, H cross k is the momentum, and also, so we equated it. So H cross or bar, as you know, is the H by 2 pi, where H is Planck's constant. You know that is Planck's constant. So we use it, solve for V. When we solve for V, we will get M by, sorry, it is H bar K by M. So it is, we have to solve for K. Clear it, because we want to go from K to V space. So we'll solve for V. V is H bar K, or H cross K as we call it, by M. So V is solve for V. No, I have to solve for K. K, let me write. Or K is MV by H bar. I need this. H cross K is MV. You can write V is equal to H cross K by M, right? Or K is equal to MV by H cross. Then what you do, you find your delta K. First you find K square. Our K square is MV by H cross square. What about delta K? Our delta K is M by H cross or bar delta V. Let me write it neatly. Delta V. So delta K is M by H bar delta V. Now, in order to go from G of K delta K to G of V delta V, what you do, making use of this transformation from K to V, H cross K is equal delta V. Here, let me use another color here. You have to make substitution for K square. Let me highlight it. That means you have to plug in K square here, right? You have to plug in, let me use another color, I think pink. You have to take this delta K and put it here. So you plug in K square, you plug in delta K, then delta K will come in terms of delta V and K square will come in terms of V square. The resulting expression which you get will be the expression for G of V delta V. Once you do that, you put it here, G of V delta V. Then you have to put for A. What's our A? A is N by Z. Let me add a page. A is N by Z, where Z is, which we solved for in the last lecture, but Z is V times 2 pi M K B T by H square raised power 3 by 2. So our A is N by Z and Z is V times 2 pi M K B T over H square whole raised power 3 by 2. And our E of V, that is the energy as a function of speed, is simply the kinetic energy of the gas molecule, half mv square. So when you do that, our equation 1 will give us, I will write that. Then, so using in equation 1, sorry, we get we get N of V delta V is CV square exponential of minus mv square over 2 kbt times delta V, where C is 4 pi n times m by 2 pi kbt whole raised power 3 by 2. Let me check it. nv delta v is cv square exponential of minus mv square by 2 kbt times delta v, and c, where c is the symbol for 4 pi n times m by 2 pi kbt raised power 3 by 2. It's okay. Let me first encircle it. Why is this? No. Let me encircle it. Let me use this red color for encircling it. First, I want to encircle this equation. Let me put it in this box. And let me get another box here. Right. Let me get my pen back. Use some other color. Okay. Then this is my equation second. This is my equation third. What I told you, this. This is our equation 1, and of v delta v, that is g of v times delta v times fi. Fi is the Maxwell Boltzmann distribution function. So what you have to do, you have to first transform this g of k delta k. How? You have to make the transformation from k to v using this h cross k is mv. Then you find v square, k square and delta k, put it here, plug it here. You will get the g of v delta v. Then you have to take a equal to n by z, where z is this, and e of v is half mv square. All this, when you put it in equation 1, you will get the Maxwell-Boltzmann distribution of speeds, n of v delta v as this. So you have to check it. All this you have to do at your places and check. You get this. Check this at home. So this equation 2 is the required Maxwell-Boltzmann distribution of speeds. It was originally obtained by Maxwell, and you can see entirely this is a classical result, as you can see by the fact that Planck's constant h appears nowhere in Maxwell-Boltzmann distribution of speeds equation 2. Actually, z contains h cube in the denominator, but when you make the transformation from k to v, you will get another h cube. Those two h cubes will cancel out, and our Maxwell-Boltzmann distribution of speeds expression 2 is without Planck's constant. So it is a classical result. Now, this distribution of speeds has some properties. We want to specify them. First, we will draw a diagram. Then we will talk more about it. Let me draw the figure. Oh, I think I will use another color here. It means the green color. We have a plot on this side, n of v. On this side, I plot v over vt. I will define my symbols. Let it be here 1. Let it be 2. Let it be 3. Let me use another color for the curve. So it is between, I will draw the figure first. Actually, it is difficult to handle this magnetic pen. One thing is this, then use another color here, black. Then I have another thing here. You can check this diagram in any book. We use red. Let me draw the curve now. This goes like this. Comes down like this. Now let me figure out other things. First, let me name it figure 1. Here, v is the speed and vt is representing kbt over m raised power half. So it is square root of kt by m. So vt is kbt over m raised power half. Now, there are 3 different but representative speeds which we will indicate in the figure first. Here, one speed is that's called Vmax. Then the speed pertaining to this black line is V bar, and the speed pertaining to this red line is VRMS. When you can do the calculations as well. Now this Vmax turns out to be √2 times V of t, Vt, where Vt is under root Kt by m, and this Vmax is the most probable speed, most probable speeds, most probable speed, I should say. So it corresponds to the maximum in this curve when we plot this n of v versus this ratio v by v of t. The maximum of peak will correspond to this most probable speed v max, and it turns out to be equal to square root of 2 times vt, where vt is kt by m raised per half. You can check it, then I should say prove it. Then this another speed v bar is what? It turns out to be equal to square root of 8 pi times v subscript t. It is the mean speed of the molecules. Mean speed or average speed of the molecules of the gas. And third thing, it was the mean speed of the molecules, square root of 8 by pi times v of t. Then we have root mean square speed of the molecules, VRMS, which is square root of 3 times Vt. What it is the root mean square speed. Let me adjust my pen. It is root mean square speed. So I will give you home assignment here. Use this, the expression for Maxwell-Boltzmann distribution of speeds, and from it, using the definition of all of these three speeds, prove these three results at home. So prove these results at home. You have to prove that the maximum speed, that is the most probable speed, that is peak in this distribution curve, is square root of 2 times v of t. Mean speed of the molecules is square root of 8 by pi times v subscript t, where vt we have represented kbt by m raised per half, and root mean square speed is square root of 3 times v subscript t. Then next thing which we have to discuss, let me use another color. The evaluation of mean square speed is important. Mean square speed. Mean square speed means VRMS square, right? So this mean square speed has a particular significance to the thermal properties of a gas, since it proves that the average kinetic energy per molecule, which I denote by epsilon bar, is m by 2 VRMS square, right? So this average kinetic energy per molecule in an ideal gas comes in terms of this mean scat speed, and it is equal 3/2 kBt at temperature T. You might be knowing it. We name it equation 4. Then another thing we want to highlight here is, as you know, the gas is isotropic. That means every direction is the same with regard to the motion of gas molecules. So this gas has no net velocity. That means half m Vx square average is same as half m Vy square average is same as half m Vz square average. Think about this. I'm saying since the gas molecules are not preferentially moving in any direction, gas is isotropic, gas has no net velocity, that means the kinetic energy, average kinetic energy along x is same as along y, same as along z, they're equal. Therefore, I can write it equal to m/6 V RMS square, which is half of kT. You can check it. Because it is 1/3 of this, m/6 is 1/3 of m/2 VRMS square. That means it is 1/3 of 3/2 kT, which is half kBt, right? So this is an example of the classical law of equipartition of energy. You might be knowing this result, law of equipartition of energy. According to which each degree of freedom of the system, here the translational motion of each molecule in each of the three dimensions of space contributes half kBt to the internal energy of the system. Remember, as I told you, law of equipartition of energy, I repeat, says that in equilibrium, in thermal equilibrium, each degree of freedom there is associated an half kBt energy per molecule or per entity in general. So here we showed that since the average kinetic energy per molecule is 3/2 kBt and there is no preferential direction, therefore this gas molecule has 3 degrees of freedom because it is translating along x, y, and z, and there is no preferential direction. They are equal, these average kinetic energies. They are all equal to half kBt. That means per degree of freedom, there is associated half kBt energy. So total it becomes 3 times half kBt, right? So this is all for today. So before leaving you, I will summarize today's lecture. So today we talked about the Maxwell Boltzmann distribution of speeds. So I gave you the idea how to get it. Then I gave you homework here to check it. I talked about the procedure and I wrote the expression directly. You will check it. Then I discuss the three speeds and I gave you homework to prove these three results. And I talked about the law of equipartition of uh, energy, which follows here from the Maxwell-Boltzmann statistics. So this is all for today. Don't forget to like, share, and subscribe my channel. If you have comments, you can any queries, you can comment. Thank you. Assalamu alaikum.